Alright guys, so this is going to be the video for our homework problems chapter number 4. So that way you guys can kind of see which ones you missed, and the ones that you were doing for practice problems as well, you can kind of see how to do those, just so that you guys can, do better on them or learn from them and all that good stuff. So for chapter number 4, we did problems 7, 11, 14, 15, 19, 24, 29, 45, 52, and 57. So we're just going to run through those here real quick. Let me make sure I'm on the right chapter and stuff here. So the first problem that we had here was problem number 7. And it says, I think this is just one for the free body diagram, so I'll run through this here real quick. The ladder shown is supported by a smooth frictionless vertical wall and is pin connected at point A. That's a key thing there, pin connected. The ladder has a length of 16 feet and supports a weight W, big W, at point C. Assuming the weight of the ladder is acting at its center of gravity, sketch the free body diagram for the ladder. So the thing about this problem, well, let me see. So for the actual ladder itself, I'm just going to draw something that looks like this. All right. The next thing that I can figure out is that we have a pin connected support at the bottom there. They did give us that information. And anytime, if you guys remember the table that I showed you, what page is that on here? Straight from the book, page number 64. It's in chapter 4, page number 64. When you have a pin connected support, that's a letter D in that table. We actually have two forces on it. So we have a force in this case going something like probably something like that there. And then we also have a force kind of acting along parallel with the ground floor. I'll just say this is reactant force A in the vertical. This is reactant force A in the horizontal. Next thing that we do know is that we have a weight of the actual ladder itself. And this ladder is 16 feet long, so half of that would be 8. So therefore, since we know that point C, let me draw it up here, point C right here, they said this was 10 feet away. I just want to add these in there. We know that point C was 10 feet away, so therefore 8 feet for our center of gravity is going to be probably like right here. So I can just draw a line straight down, and this is just going to be the weight of the ladder. And then of course, since we are kind of given this one here, we can just add that to our free body diagram. This is just considered to be W. And then the last one that we have is going to be at location B. B is not pin connected, even though it has that black dot there. They're just showing you that that black dot is B itself. It's not pin connected. It's not roller connected. It's really just leaning up against the wall there. So therefore, we just have the wall kind of pushing back on it. And I'll just call it F of force. Just have the wall kind of just pushing back on it, and then that's about it. So this one here would be our free body diagram, and then we'll be good to go from there. What problem number? This is 7, right? Yeah. Problem number 7 is complete. So next, we would have problem number 11. Number 11. And number 11 states to calculate the reactions of the two smooth inclined planes against the cylinder shown. The cylinder weighs 100 pounds. So we have what we call here a cylinder. I'm going to get fancy on you guys and actually throw in, if I can find it, where is it at? throw in a shape. I was already on it. Throw in a shape. Boom. My perfect circle there. I don't need you. So yeah, now I can actually draw what these are here. So this is going to be something like that. Even though I just kind of messed up my circle, right? This one's going to be something like that. This is going to be the ground plane. This is going to be 30 degrees. This is going to be 40 degrees. And then we have the actual weight of our cylinder, which is 100 pounds. All right. So we do know, since this is leaning up against these two surfaces there, we do know we have some additional forces. I'm actually just going to kind of redraw my free body diagram out here like this. We have a force acting on the body there, a force acting on the body there, and we have a downward weight force happening there. This is FB. This is FA, or you call it F1, F2. It really doesn't matter what you call it, as long as you keep them satisfied in this case. And one thing I also want to do is just kind of draw up here something like that, just so we can also keep all of this in order. Because I want to make sure that my angles are correct. So here, right in between here is going to be my 30 degrees, and then right in between here is going to be my 40 degrees. Again, this is not drawn to scale, definitely not drawn to scale. And so yeah, so now I can kind of solve for this problem for my forces that are acting on this cylinder. First off, again, as always, I'm going to start off with my forces. So forces in the y direction, that's going to be in equilibrium, which is 0. And that's going to be FA cosine 40 minus 100 plus FB cosine 30. All right, and basically all we did there was just kind of break these up into their two components. So we got FB in the X, FB in the Y, FA in the Y, FA in the X, like so. And so that's what these are over here. FA cosine 40, that's just going to be our FA in the Y. FB cosine 30, that's going to be our FB in the Y. Alrighty. So now we can go ahead and what's it called? Rearrange this equation here a little bit. Not much really, but we can actually turn these into better numbers so we can see them. So we have 0.766 FA minus 100 plus 0.866 FB. And then if we do the same thing for the sum of all of our forces in the x direction, make them equal to 0 so that they are in equilibrium, and then add them up, which we get FA sine of 40 minus FB sine of 30. We aren't going to be using W, the 100 pounds this time, just because that is only in the y direction, not in the x. We are only looking at the x direction currently. So therefore, we can rearrange this again, which would be 0.6428 times FA minus 0.50 times FB. Again, this is all equal to 0. And with that, we can actually solve for FB. So FB would just be, how do I want to write this? Just put a little arrow there. FB is just going to be equal to 1.2856 FA, which 1.2856 I just get from taking 0.6428 and dividing that by our 0.5. Once we bring everything over to the other side of the equation. All right. So from there, we now have an equation here with FA and FB in it. Call that 1. Also have another equation here with FA and FB in it also. Call that 2. And so therefore we could say that we can bring this equation down and say 0.766 FA minus 100 plus 0.866. Now remember FB, we just solved for, we can't solve for FB, so we can just say FB is now equal to 1.2856 FA. And so now what we have is FA only in this equation. So it'll be real easy to just pull FA out and solve for FA. And when we do that, we get FA equals 53.2 pounds. And then now that we solve for FA, we can actually take this one guy here now. And I want to just try to see. I'm actually just change the color a little bit. We can pull this out and say that FB is now equal to 1.2856 times our 53.2 that we just solved for, and FB comes out to be 68.4 pounds. Alrighty. Next, that was number 11. Next we have number 14. And number 14 states, 4 concurrent forces in equilibrium act at point C. A truss joint as shown. The 15 kilonewton force acts vertically. Determine forces F3 and F4. So I have number 14. Looks like this. I'm just trying to see the best way to draw this. Could we all have this is in the Y direction, this is in X direction. Get my forces here. We got forces coming down this way for 15 kilonewtons. We got another force happening this way for 5 kilonewtons. This here, they give us this information, which is 12 and 5. We also have F3, which is 40. And then lastly we have F4, which is 60. Once I see stuff like this, the 5 and the 12, I always like to just go ahead. I might not need it, will need it, but I would just like to just go ahead and kind of solve for that hypotenuse. So remember, a squared plus b squared equals c squared thing. So I'll just take the c is equal to the square root of 5 squared plus 12 squared, and therefore c c is equal to 12.17. So that's 12.17. Just in case I might need it. And then remember, since these are angled forces there, we have our components. Our components this way. components that way. Components that way. And this will be F3Y, F4Y, F4X, F4X. I guess I'll just call this 5 in the Y, 5 in X. You know, I don't really like calling it 5. I'm gonna just call it F2. This is gonna be F2, and this is gonna be F1. So this is just gonna be F2Y and F2X. And of course, F1 is only acting in the Y direction, so we're just going to leave that one alone. So now for the fun part, actually solving the problem once we got a couple of housekeeping items out the way. The sum of all the forces in the X direction is going to be equal to 0 to keep in equilibrium. These are going to be negative 4.93, which is, you know, the this is X direction, so F2 in this case. What's it called? Cosine or sine of, well, no, because we don't have an angle. So we have to, what is it, 12 divided by 12.17, I think it is. 12 divided by 12.17. And that'll give you that 4.93 plus F3 cosine 40 minus F4 cosine 60, and that equals nothing yet because we have two unknowns. So F3, F4 is both our unknowns. I'm going to leave that one alone for right now. Jump over to the sum of the forces in the Y direction is equal to 0 to be in equilibrium, and we have negative 15 going downward. That's my F1. Then we have minus 0.822. That's going to be my F2 in the Y direction. F2 in the Y direction is 0.822. And then we're going to add in my F3 sine of 40 plus my F4 sine of 60. So now I have two equations, two unknowns, so I can actually solve for this. This would be my equation 1, this would be my equation 2. And I'm hoping you guys are kind of familiar or aware how to do this. My last video was like over an hour long, so I'm trying not to make this one that long as well. But F3 in this case would be equal to 12.37 once you kind of rearrange this problem to solve for F3. And then once you solve for F3 on one equation, you can bring that back into the other equation, solve for F4, which F4 we get 9.08 kilonewtons. If you do this portion up here is just mainly math, solving for two equations, two unknowns. If you need some help with that, please do let me know so we can kind of run through a couple of problems that's kind of like that. But essentially these are you know, fairly straightforward there. All right, so the next one is number 15. The beam shown carries vertical concentrated loads. Calculate the reaction at each support. Neglect the weight of the beam. So we have this beam here. Boom. We've got that. Boom, boom, boom. This is going to be B. This is going to be A. We got a couple of forces happening on here. Got 5 kips. 14 kips, 6 kips. We got some distances happening here. This is 3 feet, 7 feet, 6 feet, and then lastly 4 feet. And then the total, which we can kind of guess by adding up all this math, is a whopping 20 feet. And it wants to calculate the reaction at each support. So our reactions in this case is going to be RA in the vertical, RA in a horizontal, which in this case is going to be equal to 0 because you have nothing else happening in the horizontal. So in order for it to be in equilibrium, it must equal 0. And then we're also going to have RB in the vertical. So easiest thing to do in this case is honestly the moments. So moment at A is going to be equal to RB times 20, which is a distance. Remember, moment is equal to the force times the distance away from that force. I probably shouldn't write it like that. I'm gonna write it like this, where it actually stands out. Moment is equal to force times distance. So we have force times distance. Only thing you have to really keep in mind is the direction that is being rotated. So RB is positive because it's making the whole entire system rotate counterclockwise. Counterclockwise is positive. And then all the rest of them are going to be negative because it's making the entire system rotate clockwise. So minus 5 times 3, minus 14 times 10, minus 6 times 16. Again, all these distances come straight from location A. And that's going to be equal to 0 to be in equilibrium as always. And then we can solve for RB, which is 12.55. I probably shouldn't put that arrow. Oh, I'm going to do this. I'll do that like that. That way you don't get confused, because this is RB is actually going up. It's a positive force going up. And yeah, so from here you could actually solve the next portion of it just by adding up all your forces, subtracting RB, or you can, I just wanted to do this because we haven't done too much on moments yet. We can do the moment about B itself, which is going to be equal to minus RA times 20 plus 5 times 17. And remember, now it's kind of flipped because we're taking the moment about B. So that means B is our center point, and then RA, the reaction at A, is actually pushing it up and to the right, so that's clockwise. But everything else, all the other forces, the 5, the 14, the 6, is pushing it downward and to the counterclockwise rotation. So counterclockwise is positive. That's why these are now positive. So plus 14 times 10 plus 6 times 4. I think I got them all there. RA 5, 14, and 6. Yep. Again, this is an equilibrium. Set it equal to 0. And therefore, RA is now equal to 12.45 kips. And this is also going up in a positive direction. And that's it. All right. Was that 15? So next up is 19. Problem number 19 here. And 19, let me switch the page. 19 states to calculate the reaction at each support for the truss shown. Neglect the weight of the truss itself. Let me just draw this truss first. This is going to be a boom, 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 boom. The only thing I need to connect now is this and that. Then from there we got, whoops, thought I changed this to red. From there we got 4 kips coming down straight in a Y direction, 8 kips coming down straight in the Y direction, 5 kips coming down straight in the Y direction, and then lastly 12 kips coming down straight in the Y direction as well. And then of course we have some reactions here at location A. and location B. And those reactions are going to be for the roller, straight up, for the pin, up and over. But again, as we know, with this being everything in the Y direction, that means the X is going to be 0. So I'll just write RAV, RAH, RBV. And I've got a couple of distances here. So this is 15, 15, 15, 15. For a total of 60 feet. Yep, these are all feet. All right, so now we can jump into actually solving the problem. Again, fairly straightforward, especially since we know how to work our moments. Sum of the moments at location A is equal to RB. In this case, it's technically RBV, but it's really the only RB anyway. Times 60 minus 4 times 15 minus 12 times 30 minus 5 times 45 minus 8 times 45. And that's going to be an equilibrium. And therefore, we can solve for RB is equal to 16.75 kips going straight up. MB is just equal to minus RAV. Again, minus only because it's making the whole entire system rotate clockwise, and that's 60 feet away, plus 4, which is 45 feet away, plus 12, which is 30 feet away, plus 5, which is 15 feet away, plus 8, which is 15 feet away, equals 0. And again, all those are positive because they're making the whole entire system rotate counterclockwise. So therefore, RAV is equal to 12.25 kips going straight up. All right. So what was that? 19? No. Yeah, 19. So after 19 was 24. So let me get my paper here. So 24. Chapter 4, number 24. We have determine determine the reactions for the beam shown. The beam has a pin support at one end and a roller support at the other end. Neglect the weight of the beam. So we have a beam here. We have a support here. We have a roller support there. Let's put our forces in before our distances. All right. So solving this problem, number 24. Same scenario that we usually do. I'm just gonna draw this real quick. because we got our, forces in the y, forces in the x. Whoops. And so one thing I will say is that in this case we do have a force in the x direction here. This is a force in the y direction. So for our reactants here, we have this reactant right here, which is going to be RB in the V. We also have RA in the V. Then we also have RA and H. And so therefore our sum of our forces in the x direction is equal to minus RA in the H plus 400 what's it called? 400 cosine 60. And the reason why RAH is negative is because since you have a force going to the right, you need to be in equilibrium, so that means you have to have a force going to the left to counterbalance that. So this one would technically be going to the left. So that's kind of like just a head thinking there. If you got a force, this is for sure. You don't know which direction RAH is going. That's kind of guessing. But you know for sure that the force they give you is going to the right. So therefore you can kind of guess and figure out, RAH in this case. And so therefore you can solve for, and this is going to be equal to 0, make it an equilibrium, solve for RAH, and this is equal to 200 pounds. From there, you want to solve for sum of your forces in the vertical y direction. And we have sum of the moments at A is equal to RB times 20 minus 120 times 2 minus 800 times 10 minus 400 sinus 60 times 17. All that being equal to 0, to be in equilibrium. And RB, sorry. RB is equal to 706. And if you do the same thing but at the opposite end, so moment about B, you'll get RA in the vertical this time times 20 plus 120 times 18 plus 800 times 10 plus 400 sinus 60 times 3. That's going to be equal to 0. And so therefore RAV is now equal to 560 pounds. Alrighty. After 24 was 29, it looks like. So let me grab that one. Number 29. And this problem says to rework problem number 4.28, assuming that a point D has been elevated so that the cable DB makes an angle of 15 degrees with the horizontal. All right. So a few things. So we got a graph from 4.28 is the mass. The mass is 300. I just want to write that. Mass 300 kilograms. And supported by a boom as shown. Determine the tensile force in the cable and the reaction at A. Okay, so therefore we have I'm just gonna draw this here. So we got that. And let's see. I was trying to think of the best way. Sorry, I'm just trying to think of the best way to draw this with the elevation on there. So that cable DB makes an angle of 15 degrees. Alright, so I'm thinking DB is just going to go up because the location A is pinned to the ground. Yeah, so I'm thinking, okay, yeah, because they said point D has been elevated. Okay, sorry, I was kind of confused. So if point D has been elevated, that means it's going to come down, look like this. And then I think they said that this is what, 15 degrees here. 15 degrees with the horizontal axis. And so therefore this would be our object here, like so. This would be our weight coming down like so. And then this would be our A at here. I can't really tell if A is determine the tensile force in the cable and the reaction at A. A kind of looks like a roller just because it's a circle, but I don't know, it might be a pin. Yeah, I think I'm gonna take A as a pin. A, it looks more like a pin than a roller. Just like this is kind of somewhat like an arc-shaped pin or something like that. So, with that being said, the forces that we have on here is probably going to be something like this, something like that. We do know that, of course, this is going to be a force in the y direction, just as well as a force in the x direction. And yeah, and I'm sorry, this is not force, this would be considered tension. It's a cable. Cable is considered tension. Just want to make sure we get that right. Tension in the x, tension in the y. And tension in the y is going to be T sine of 15. Tension in the x is going to be T cosine of 15. So sum of all of our moments at A is equal to T cosine of 15 times 2.6, which I kind of forgot to add in those values for you here. So the values that they give you is more at an angle versus straight up. And this is also, let me finish drawing this off first before I continue on. This is also 60 degrees. That's 3 and 2, so this is 2, is that meters, right? Yeah, 2 meters. This is 3 meters. But with that, you can also solve for what is the horizontal and vertical. So, and I'm actually going to draw that in a different color. I'm drawing it in pink. And this is going to be 1.5. And then this one here is going to be 2.5. And then from the height of it here, I'm actually going to make the height come out this way. It's going to be 2.6. And that should be it. That should be it. Excuse me. All right, so what is this? So the moment at A is going to be t cosine 15 times the 2.6 plus t the sine of 15 times the 1.5 minus 2.94 times 2.5. And it's in equilibrium. And then once you kind of break this up to solve for t, so we got one unknown in this case, t, in both of these problems. So t equals 2.54 kilonewtons. And again, that's just solving for t in this equation here. If you wanted to, you could solve for ty and tx. So remember, you can just bring this over here and plug into both of these equations there. All right, so now we have t, and I did go ahead and do that. Ty is equal to 0.657 kN. Tx is equal to 2.45 kN. So what about the forces in the y direction? Well, we can do that by solving for A in the vertical. I really should say RA in the vertical, RA in the horizontal, RA in the vertical. So RA in the vertical is going to be plus 0.657, which is my T in the vertical, minus 2.94, which is my weight coming down. And so therefore, solving for R, again, this is going to equilibrium, set to 0. Solving for RAV, you get 2.28 kilonewtons. Sum of the forces in the x direction is going to be equal to our RAH this time, minus 2.45, which is our tension in the x direction. And then we're going to set all that equal to 0, and then make sure we solve for RA in a horizontal, which gives us 2.45. I don't know why that was something missing there, but yeah, it's only just RH minus 2.45. Bring your 2.45 over to the 0 side, and then you just get 2.45. Cool. So yeah, so from there we solve for our R about A, which is 2.28 squared plus 2.45 squared. And then we get 3.35 kilonewtons. And then our theta is going to be equal to the arctan of 2.28 over 2.45 the y over the x, which is going to give us 42.9 degrees. Alrighty. So yeah, so from there we have problem that was 29, right? So after 29 is 45. So this is 4.45. And then we just got two more after that. So problem 45 states, turn 2 pages there. A rod of uniform cross-section weighs 4 pounds per foot and is pin connected at point A as shown. The rod supports a load of 48 pounds at point B and is held horizontally by a vertical wire attached 2 feet from point B with a force of 85 pounds in the wire. Determine the length of the actual rod itself. And I think this is the image here. So I'm going to draw this. This is A. We're going to go ahead and just draw. This is supposed to be straight. Sorry, I kind of made it at an angle on accident. Alright, I think that's really all the information that they give us at the moment, other than, you know, inside the problem itself. So for this problem, one thing that we do know on this problem with a force of 85 pounds on a wire. Okay, so yeah, on this problem here, we kind of have to determine a few things, which is not too hard to determine. We just got to make sure that we, I guess, determine them correctly per se. One thing I do want to mention is that the wire says it has 85 pounds on it of a force, so I just want to, like, just so we don't forget about that. Force of 85 pounds on the wire. So yeah, honestly, the easiest thing to do for this problem here is solving for the moments about A, and then we can get L. That'll be the easiest thing, because, you know, remember, force times distance equal m. So we do know we have a force of 48 and a distance away of L, so we can just solve for that by the moment. That'll probably be the easiest thing to do in this case. So the moment is equal to minus 4L, and I forgot to actually write that on there. That's why I was kind of confused, because I was missing something. But so for this problem here, they give us the weight of the object. So the weight of the object is going to be pounds per foot. So it's going to be basically right in the center. I'll just call it W for weight, and pounds per foot for pounds per foot. We don't exactly know what that L is, so in this case this would be 4L L over 2. So that's the distance away, L over 2. And then we want to add in there our 85. And 85 should be clockwise. I know 85 is pulling up, so to make it go counterclockwise. Okay, just want to check my signs. And that's going to be L minus 2. So L, total distance L minus that 2 feet away from B. And then we have minus 48, which is the main thing that we look at, times L. That's going to be equilibrium. And after a little bit of arranging this problem here, what we will have is minus 2L squared then we're going to add in there 85L. We're also going to subtract 85 times negative 2, which is 170. And then lastly, we're going to minus 48L. And then from there, we want to continue forward, just trying to minimize this a little even more. We want to divide everything by 2 and combine. So we want to combine like terms, 48 and 8. And then we want to divide everything by 2, so we get L by itself. So now we have L squared minus 18.5L plus 85. So again, all we did was combine like terms, and then took our 2L squared, divide everything by 2, and we get that. And then from there, we can use what they call which we haven't used in a while, but remember we mentioned this in, I believe it was chapter 1 or chapter 2, 1 or 2, quadratic formula. If not, this is this is something that you guys learned way back when in high school and whatnot. Quadratic formula, when we have something to the power squared times another variable times that. So therefore we can use the quadratic formula, which we get b plus or minus the square root of b squared minus 4ac all over 2a. And then once we do that, we can easily solve for our L value. And L is going to equal to 10 feet, or it's going to equal to, and I don't know which one in this case, 8.5 feet. So this is one of those math things. You need any assistance with this, let me know so I can kind of give you a brief overview of this as well. But hopefully you kind of get that there. All right, so after 45, we have 52, then 57. 52, problem number. Show the reactions at supports A and B for the tower shown. So the tower shown is going to be So the shower stone is going to look something like this. This wonderful drawing here. We got 4 bays at 16 feet each for a total of 64 feet for all the bays. And then I'll give a total height of 30 feet. Then we're just supposed to just find the reactions at the supports. Which I should probably draw those as well. You got a support down here. Support down here. And essentially we're just finding the moments. Moment about B is equal to 10 times 48. And then we also want to add in there the moment about B for another force for 4, which is times 30 minus 15 times 16 minus, I'm just going to call it RAV times 16. And remember RAV, this will all be equal to 0. This is going to look something like this. So we got to make sure we add those in there. So MB, just to kind of make sure we're all on the same page. The moment about B, which is this point here, and whoops, I meant to grab green. This point here in green, that's the moment about B. We have a force that's 10 feet away. I mean, a force that's 48 feet away. That's this guy here. We also have a force that's 4 feet away, but this one is going to be vertical, but it really doesn't matter. It's still the same thing, 4 feet away. That's 30 feet, 4 feet or 4 kip force, which is 30 feet away. And then we also have a 15 kip force right here, which is only 16 feet away, which is this one here. And then we also have a reaction at AV, which is right here. That's 16 feet away. So everything is based off of our center point of B here. And so therefore all of our forces are going to be based on that. And when we calculate for what's the only unknown that we have here, we have RAV as our only unknown. So we can calculate for that being 22.5 kips. So now that we have that one, we could go through and do some of all of our moments at A. But with all of these different forces, why not just make life easy by just doing the sum of all of our forces in the x direction, which is going to be equal to 0. In the x direction, what do we have? We have 4 kips, negative 4 kips, plus RAH. So therefore, RAH is equal to 4 kips. And then same thing for some of our forces in the y direction. Make life easy. We can do this to solve for RBV. So we have negative 10 plus 22.5 for our RAV minus 15 plus RBV. I think that's it. 10 RAV, RBV, 15. Yeah, so those are the only ones in the y direction. So RBV is just equal to 22.5 minus 10, which gives us 12.5 minus 15, which gives us what, a negative, no, 22.5. Let me grab my calculator. Negative 10 plus 22.5 minus 15. Okay, yeah, so negative 2.5. Um, 2.5. See, I'm trying to see why I got a negative. I must have mixed up something. Oh, I know why. Because I forgot to set all this equal to 0, so it really would be positive 10. Yeah, because I got to get RBV by itself. Sorry about that. RBV, to get that by itself, I would take all this stuff and throw it to the other side of the equation. So then it would be positive 10 minus 22.5 plus 15, and I would get a positive 2.5 value there. Okay, that makes sense now. So 2.5, that's Kips there, which makes sense because 22.5 for our AV plus 2.5 for our BV should equal our 10 kip plus 15 kips, which is 25 kips there. All right, and so the last one is going to be number 57. And then we'll wrap this up here, 57. And make sure I get to the right page here. A horizontal beam is pinned connected to a wall at one end and braced diagonally at point D as shown. The beam carries a uniformly distributed load of 800 pound-feet and a concentrated load at its free end of 500 pounds. Determine the horizontal and vertical components of the reaction at point A and the force in member VD. Neglect the weight of the members. So let me just draw this here real quick. But one thing that I'm noticing about this problem is that we really don't need to draw the entire thing. I'm going to draw the entire thing anyway. They got this thing here. They've got B here. They've got A here. They got a distance from A and B of being 9 feet. They've got an object here off of A. They're calling this C. And at C, we've got a 500 pound force there. We also got a uniform distributed load thing going on here. With a W of 800 pound per feet. So that means to tell me that big W in this case is going to be, what's the total length of this? 12 plus 4, right? Because we've got a situation at D here, from D to B, and from D to B, yeah, so therefore big W is going to be 12 plus 4, which is 16, so 800 times 16, and that comes out to be 12,800. All right. Anytime I see uniform distributed loads, I automatically want to just find the weight. May need it, may not need it, but just get out the way now. And so therefore, that's 16. So then this is our, I'm gonna just call this W2. And then the distance, since that's 16, is gonna be 8, which is half of 16. Alrighty. So yeah, so really we don't really need all this information. We need a lot of it, but not all of it. So it gets a little messy at that point. So I'm just gonna come over here. I'm gonna draw my free body diagram for this. Because really all we need is this guy here. And then we just add a couple of forces on there. We know A, we know that. We know BD is happening here, which in that case is doing something like this. So this is going to be BD. This is going to be BDY. BDX, AY, AX. This is going to be 500. And then we also have W, which is 12,800. And so the reason why I would say that we don't really need everything here is because of the question what they're asking. They're asking to determine the horizontal and vertical components of the reaction at point A in member BD. And the force in member BD. So just the force in member BD and also the vertical components of reaction at point A. So we really don't need the information at location B for this. So you can kind of like minimize what we have here just to kind of make this problem seem a little bit simpler. But yeah, so sum of the moments about A is going to be equal to minus 12,800. Remember, sum of the moments to find reactions is the easiest thing to do. That's going to be times 8 plus BDY times 12 minus 500 times 16, all equal to 0. And therefore, one equation, one unknown, BDY equal to 9,200 pounds. BD in the x direction is going to be equal to 9 over 12 of BD in the y direction. And we get this because we do know that, or should I use green? I use green. We do know that, you know, the distance, how can I draw this? Boom, boom. We know that this is 9 from right here. We also know that this is 12 from right there. So if we do our, you know, equation there, it's a Pythagorean theorem, whatever it's called, that's gonna, this right here is going to be the 15. And so therefore, if we want to solve for our equation, we can kind of set it up, you know, with the law of sines. Utilizing the law of sines in this case, we can do 9/12 of BDY gives us BDX. And so therefore, BDX is equal to 12,270. Now, if you want to find BD by itself, therefore we can just do 15 over 9 BD and the y. Again, this is all with the law of sines. We got 15,330 pounds. And so then from there we can solve for our sum of the forces in the x direction, which is our RA in the horizontal, or y. I mean in x. I'll just put horizontal. Hopefully that doesn't confuse anybody. RAH, horizontal is the same as x, plus BDH. Therefore RAH is equal to BDH. And we solve for BDH already, which was right here, BDX. BDX is BDH. Yeah. I'm just going to write that also, BDH. And then this one, BDY. Or, sorry, vertical. So that's 12 to 70. And sum of the forces in the y direction is equal to RA in the vertical minus 12,800 plus 9,200 minus 500. And so therefore RAV is equal to 4,100 pounds. All right, so that's the last problem there. Problem number 57. Again, if you guys have any other questions at all, please do not hesitate to ask me. I know a lot of times students say that when I do it here, it makes all the sense in the world, but when they do their homework problems, it makes no sense. So please do reach out to me if you need to beforehand. And if not, you guys have a wonderful rest of your day.